Ranking a long list of competing priorities all at once strains our working memory. But if we break that list down and only compare 2 items at a time, we can focus on the specific nuances of a single relationship. Mathematician Thomas Soddy built an entire decision-making framework around this psychological insight. He realized that our subjective gut feelings could be quantified if we isolated them into simple pairs. This table shows Soddy's fundamental 1 to 9 scale, assigning a strict number to human preference. 1 means equally important, 3 is moderate, and 9 represents extreme importance. To apply this to a real decision involving cost, quality, and visibility, we set up a 3x3 matrix. By combining this blank grid with the 1 to 9 scale, we have a system that can convert our subjective opinions into measurable quantitative data. The first step in filling out the matrix is establishing our baseline. Comparing any criterion to itself always equals 1. Since a cost is exactly equal to a cost, we place 1s straight down the main diagonal. Now we make our first real judgment. If we decide that cost is 4 times more important than quality, we place a 4 in the cell where the cost row meets the quality column. This brings us to a strict mathematical requirement called the reciprocal rule. If cost is 4 times greater than quality, then quality must be exactly 1/4 as important as cost. We place a 1/4 in the reverse cell. Let's test this logic. Pause the video for a moment. If you decide that quality is 5 times more important than visibility, where do the numbers 5 and 1/5 go? The 5 goes into the intersection of the quality row and visibility column. The 1/5 goes into the reverse spot, the visibility row and quality column. The reciprocal rule enforces symmetry. It prevents us from accidentally submitting contradictory logic on the other side of the grid. With 2 of our 3 comparisons complete, we face a mathematical trap. Perfect transitivity dictates that the relationship between cost and visibility should be the product of our previous choices. Cost is 4 times quality, and quality is 5 times visibility. 4 times 5 equals 20. But a score of 20 exceeds the limit of our 1 to 9 scale. To keep the math workable, we cap the value. We place a 9 in the cost visibility cell to represent the absolute ceiling of extreme importance, and a 1/9 in the reverse cell. Human intuition doesn't always map perfectly to strict arithmetic. The Pairwise system expects slight inconsistencies and accommodates them, so you can still reach a practical decision. This matrix shows our completed set of judgments, ready for calculation. We begin deriving our final weights with step 1, adding up the numbers in each vertical column to get a sum. Step 2 is normalization. We divide every single cell by the total sum of its specific column, converting all those varied fractions into clean decimal values. Step 3 is finding the row averages. We read across horizontally, adding the 3 decimals in a row and dividing that sum by 3, our total number of criteria. Those row averages generate our priority vector. This is a new column sitting on the right edge of the grid that holds our final synthesized scores. Executing those 3 specific operations, column sums, normalization, and row averages, is how you transform a grid of varied fractional judgments into a single set of standardized priority weights. This chart isolates our final priority vector as percentages. Cost comes out to 70%, quality 22%, and visibility 8%. The matrix reveals the mathematical outcome of our initial inputs. Cost accounts for 70% of the total influence in this decision, based on the specific pairs we just ranked. The entire process boils down to a 3-step playbook. First, score your pairs from 1 to 9 and apply the reciprocals. Second, divide every cell by its column sum. Third, average the rows. Pairwise comparisons let you justify difficult choices with transparent math. But remember our transitivity trap. Because we intentionally used a 9 instead of a 20, our logic was slightly inconsistent. Next time, we will learn how to calculate exactly how much inconsistency is mathematically acceptable.